Welcome to this first session in the conference on discrete groups, geometry and arithmetic in honor of Professor Raghunathan. We have two talks in this session, the remaining, and then we'll have the second session during the day. The first speaker is Shahar Mozes from Hebrew University, Jerusalem. He is happens to be one of the collaborators of Raghunathan, and also he has had connections with India. He has worked with Nimisha, and also we have had frequent contacts and so on. It's a pleasure to welcome you, Shahar.
Thank you.
And Shahar is going to speak to us today on surface groups in some uniform lattices. The full title involves also lattices in semisimple groups, etc. So, but he seems to have put it down for to make it concise. Yeah, and it's declared to be joint work with Jeremy Kahn and Francois Labourie. So over to Shahar. For you have 30 minutes for the presentation.
Okay. So thank you very much. So first, let me congratulate Raghunathan for his birthday. I owe a lot to Raghunathan and his mathematics and his vast knowledge and generosity with his knowledge. As Danny has mentioned, I've been very fortunate to even collaborate with Raghunathan, but his influence on me goes before we met and of course afterwards. So I don't think in 30 minutes would be suffice to say how much he influenced me and how much I owe him. And I also would like to thank the organizers for the invitation. I hope that the next Raghunathan conference will be held in India and not via Zoom. I mean, that's one thing. Yeah, you can't, the Zoom doesn't have enough bandwidth to transmit Raghunathan or India. Definitely not both of them. Okay, so let's say, so just one thing that, since it's only 30 minutes, I wrote down the notes before, and I think it's the second time in my life that I give a talk that I wrote down beforehand. That's the previous one was the ICM. I'm not sure I've ever done it before, and I think it would be obvious that, not in the positive way, that I've not done it before many times. So as Danny mentioned, so this is a joint work with Jeremy Kahn and Francois Labourie. And let me actually start with a theorem which is due to Kahn and Markovich, which is the motivation for our work. In many ways, all we are doing is extending their work and some of their ideas, introducing hopefully some new ones to a more general setting. But Kahn and Markovich theorem, celebrated theorem from 2012, said that if you have a uniform lattice in PSL2C, so SO31 if you prefer, and you take then you can find a subgroup in it, which is isomorphic to a surface subgroup. And actually, they even give a quantitative version. So given some positive epsilon, then you can find some gamma G inside gamma, some subgroup, which is isomorphic to the fundamental group of a surface of genus G, so some hyperbolic surface. And actually, this surface subgroup is actually quasi-Fuchsian, meaning that you can, you can take a map from the boundary of gamma G, which is just a projective line, into the boundary of the semantic space, CP1, and which is gamma G equivariant, and the image of the boundary is 1 plus epsilon quasi-symmetric. And this is really a wonderful theorem. It has lots of important applications, just to mention people have seen it in the context of Agel's work and proof of the Haken conjecture. But what I want to report about is the generalization of this for higher rank case, where you have now a G, a complex simple Lie group. So that's the first version of the theorem. And we have again a uniform lattice. Then they claim that you can find a surface subgroup in it. You can find the subgroup of this lattice, which is isomorphic to the fundamental group of a surface of a higher genus. And now this complex simple Lie group, of course, they're not all groups. And let me just say, a priori, we don't know how to prove it to SLNR. So that's the embarrassing thing. And on the other hand, it holds in more general context than the just complex simple Lie groups. I'll maybe I'll be able to state exactly or approximately the statement, the condition we need. And another thing, so here we can just think about SLNC, and actually we prove a quantitative statement similar to what Khan Markovich did. And I'll just say very briefly here the quantitative version. I'll come back to it. And so we'll need, throughout this work, we need to fix some representation of SL2R into G. And there's some conditions on this representation. We would like it to have a compact centralizer, and we'd like it to associate with it, you have a flag manifold, which is just G modulo some parabolic subgroup, on which every element of SL2R under this representation acts with a unique attracting fixed point. And then once you have such a representation, then there's what we call circles. So circle just map from the projective line, the boundary, if you want, of the parabolic space, on which of course SL2R acts, into this flag manifold, which are equivalent under a representation of SL2R, which is conjugate to the fixed one, the one which shows at the beginning. And then if you take any triple of points on the circle, they determine symmetric on this flag manifold, right? You take these 3 points on the circle, the circle corresponds to some hyperbolic space embedding the symmetric space. If you have 3 points, it turns a point in the symmetric space, it gives you a visual metric on the boundary. So this gives you this metric. And then there's a notion which is called what's called Sullivan map, which is, should we want to somehow to be, remember in Khan Markovich, there was this quasi-symmetric maps of the boundary to of the hyperbolic plane to the boundary of the 3-dimensional hyperbolic space. So here we'll have what we call zeta Sullivan maps. So this is maps from the projective line into this flag manifold. So if you take any 3 points in the projective line, then you can find a circle. So this is a circle, remember, we call it just this type of map, which are equivalent under this sum representation. And so that you take any 3 points on the projector line, you have a circle so that the map, your map is very close to this map of the circle. Okay, so it's close up to zeta. This is, notice these are just compact set, the circle is compact set. So this makes sense only if zeta is small. Okay, if zeta is large, there is no condition, it's vacuum condition. If zeta is 0, this is just circle, just 0 Sullivan maps. And the main thing is that this will show that we'll construct a subgroup, a surface we'll construct homomorphism from a surface subgroup, from a surface group into our lattice. We would like to show this injective. And the way we show it injective, we show that associated with it will have some zeta Sullivan map, which is for zeta small enough. And these zeta Sullivan maps, I won't even read the whole statement here, come back to it later if we'll have time. It's saying that if you have a map which is zeta Sullivan, then it's corresponding to representation. It's called a Nossov representation. These are certain type of representation of SL2R into G, which we'll introduce and studied a lot by François Leboury first, but then by other people. And the main, all we need to know about them, they are faithful. Okay, so as I said, there's a quantitative version, and given the time, I think it's better to skip it right now. I'll come, if there is time at the end, I'll come back to this one. So what's the idea? How we are going to find the surface subgroup? So, okay, so we need to look at the surface. We want to see with them geometrically at the surface and to see how we can start with the surface, decompose it into simpler pieces, and then actually go back and find some kind of analog of these simple pieces inside our lattice and construct from them a surface subgroup or homomorphism from surface subgroup into the lattice. So if you think about the surface, so this is just some 2-dimensional manifold of higher genus, and you can cut it into what's called pair of pans. So pair of pans are here. Yeah, here referred to as pair of pans. So topologically, just some, you have some surface with 3 boundary, connected surface with 3 boundary components which are homeomorphic to a circle. Okay, so these are pair of pans, and it's easy to see that starting with any compact surface, you can cut it into finite pieces, which each of one of them is a pair of pans. And now this is just, just a topological surface. The word hyperbolic here is not really relevant. We'll see where it plays later. And so what we would like to do, naively, the ideal thing would be to try to look at the symmetric space. So X will be the symmetric space of our group. So G mod K, if you look at SLNC, it's SLNC modulo SUS. SUNC, and we want to look at this symmetric space and find in it many pair of puns, so things which are look like hyperbolic pair of puns, and you actually want to find them not in the symmetric space, but in the symmetric space modulo gamma, in the symmetric manifold that you get when you divide by gamma. And then you want to glue this pair of puns to construct sigma, so to go in the opposite direction, construct this type of surface. Okay, so we want to find lots of pair of puns and then to glue them together to construct a complex surface of higher genus. And then you want to show that this fundamental group of this surface that we constructed actually injects, embeds inside gamma. Well, of course, you could take just some ball in our X mod gamma and just construct a surface in there, but it will be contracted. Right? So we need to do it in a way which it injects. And this is a neat idea, but somehow we have to work with the symmetric space is somewhat too complicated. It has too much, it has a very rich structure, and it's convenient to work with with coarser objects with less structure. And sometimes this makes it harder to explain and to write, but let me try. So we're going to look at different geometric space, and we replace pair of puns by some coarser objects. So it will be quasi pair of puns. I'll explain them shortly. And then we're going to take this pair of puns and not exactly glue them together, because well, first thing, they'll not be exactly a pair of puns, but we'll approximately glue them together. So what is so let's look again more closely. What is a pair of puns? So I said the pair of puns was just topologically, it's just something which look like a disk in the plane, which you remove two smaller disks from it, and we can draw on it. You want to triangulate it. You want to cut it into two triangles, but actually two ideal triangles. So here you take this pair of puns and you draw on it. Okay, so you take suppose you think of what you do, you take and draw a curve which took actually three curves, one curve which spirals around one of this hole, and in one direction, the other direction go around this hole, and then you have this blue curve which starts at around this hole and goes out and spiral around this boundary component, etc. So you have these three curves, and then if you cut along them and I color them, they decompose this pair of puns into two connected components. So here I, painted them with different colors, so it's easier to follow them. And then you see that actually what you get are two ideal triangles, right? So just think of them in a hyperbolic plane, you have ideal triangles, so just triangles, the vertices at infinity. And so actually you can construct a pair of puns, a hyperbolic pair of puns, by taking two ideal triangles and glue them together. Now, there are many ways of gluing hyperbolic ideal triangles together, and the way we would like to do it will give us a special type of pair of puns. We don't want to look at all pair of puns. We restrict ourselves to a special shape of pair of puns. So what we do, if you look at the ideal triangle, so these triangles should be hyperbolic triangles. You can think, if you want, there are three. You can put them on the edges. You can mark special points if you want. I took a point, just a center of mass, and look at the closest points of them. You can take a point perpendicular, going from one ideal point of the boundary, take a perpendicular to the other edge, no matter how you do it. And then I want to glue the two triangles so that they are sheared with respect to one another by distance r. So we are going to fix some distance r and glue this triangle together when they are sheared distance r. So this actually will, and you do it along the three edges, match them correctly. So actually, if you take these two triangles, see here, there's a blue triangle, another one, and you shear them distance r is going to be very large, and you glue them, then you'll get a pair of puns, and actually this pair of puns looks more like this. Okay, so it's a very narrow pair of puns. Okay, so this is with the hyperbolic structure. And so we're going to look at pair of puns, and we try to build our surface for pair of puns, all of whose boundary components have lengths 2r. Okay, and we are trying to construct them. Now, this, I said that if I was continuing to work with the symmetric space, I could continue now, but now that's not exactly what we are doing. We have to work with a different space, which we'll call the space of tripods for some reason. I'm not sure it's a good name, but you think of it the following way. You think of it that you take our group G. So G will be SLN-C, but you fix a copy of it, G0, the SLN-C and SLN of an n-dimensional hyperbolic linear space over C, and you look at all the map from specific copy of G, so called G0 to G. So the space of all this map is what we'll call space of tripods, or actually tripods will be just one connected component of this space. And let me skip a little. And yeah, so we are going to fix a Lie algebra SL2R inside SL and C. So look at the Lie algebra SL2R. There's the standard basis A, X, and Y. So usually the standard basis you can take A to be just one. The diagonal matrices 1, -1, and then you have 0, 1, 0, 0, 0, 0, 1, 0. And any representation of SL2R in the Lie algebra of G is correspond to what's called SL2R triple, right? So these are 3 elements in the Lie algebra, so they have the same, satisfy this relation. That AX is 2X, commutator of X and Y is A, and A commutator of Y is -2Y. And you're going to need some assumption. The assumption that the Lie algebra, or if you want to correspond to Lie group, is compact centralizer. The element A, the semisimple element, is a regular element, and there is some technical condition we call the flip, which, okay, it's written here. Technically, what you should think of it, you take the diagonal element corresponding to A. Look at it. Okay, look at it has a large. We wanted to have a large centralizer. So if you can, there is an automorphism of the Lie algebra which fixes A in place and takes X to -X and Y to -Y. You want to be able to realize this automorphism by rotating by an element which commutes with A. Okay, this is written more technically here in papers. Sorry. Okay, so as I said, the space we are going to work with is the space of tripod. So this is replaced for us the semantic space. It's just the space of all map from a copy G0 isomorphic to G into G. Okay, so a tripod just isomorphism from G0 to G, and we fix one such tripod and look at we are only going to use the conjugate of this fixed tripod. That's the space we are going to work with. And we fix also an SL2R triple in the Lie algebra of our fixed copy of G of SL and C, this G0. So this, once you fix this gives you a map from a hyperbolic plane into the symmetric space of this G0, and you have this map from the boundary, and you have 3 specific points in the boundary, 0, 1, and infinity, which are associated with the standard basis that we fix of SL2R. Okay. Yeah. And so given a choice of this G algebra, this SL2R, every tripod, every isomorphism from G0 to G, gives us a map from the boundary, from the projective line into this flag manifold, and you have this 3 point going to specific 3 point to some 3 points on the boundary. And 3 points on the boundary, they give you a triangle, right? What we'll think of an ideal triangle. So we just schematically we draw them like this triangle. We have these 3 points at the boundary in the flag manifold. These are 3 points at the moment which comes which sit on a circle map, on a map from the projective line conjugate to G mod P, which is conjugate to our representation. And we'll just draw an arrow here to specify which is the attracting or repelling fixed point of the diagonal element. So this is called a triangle. And now we want to construct pair of plans. And this was done by taking 2 triangles, ideal triangles, including after shearing. So you have these 2 triangles, and you can define. You have an arrow going along one edge, and here this arrow. These are this arrow which appears here, and you say that they are sheared if they sit one next to the other. And if you look at this, if you take the perpendicular from this 3rd point to this edge, and from this point to this edge, the base of the perpendicular distance are apart. Okay, and all these 4 points sits on this unique circle. Okay, and then we also need some technical thing of rotating the edge, and this is just to say that what would be a perfect way of constructing a perfect pair of plans. If you take this pair of plans, there are these 2 triangles, and you lift them up. So you take 1 triangle, lift it up, you get this tau 0, and then you have these 3 adjacent triangles, which are actually the same one. You can lift them in 3 ways. You get tau 1, tau 2, and tau 3, and all this tau 1 is R sheared with respect to tau 0. Tau 2 is R sheared with rotation of tau 0, and the same for tau 3. And when you have such an object, then you get actually 3 elements, alpha, beta, and gamma in G. So these are the elements. Alpha would be an element which takes this triangle and just, if you want to rotate it, take this triangle and map it to this triangle. Beta takes this triangle tau 1 and maps the triangle appearing here. And gamma is just take this triangle, rotate it, fixing this point, taking it here. And it needs to say to check that alpha time beta time gamma is just the identity. So if you have such a 4 triangles, this gives you a pair of points with boundary of length 2r, but these elements alpha, beta, and gamma that you construct are just element in G. We would like to have such an object with elements in gamma. And this is too restricted. We can't find such elements in gamma. Otherwise, there's no reason to be in gamma. There will be a, any pair of points with all 3 bounding components of the same length 2r. So we have to allow what we call quasi-tripods. So basically, you just take the picture, the ideal picture that you described, and you perturb a little. So a quasi-tripod means that you take a triangle, a tripod, which is a really 3 points sitting on a circle. The circle is this particular type of map from the projective line, the flag manifold. But you take points which are near them. You allow kind of wiggling a little. You take 3 points which are near these 3 special points. So that would be a quasi-tripod. And this gives you enough freedom to try and construct this pair of points. Now, the way you construct pair of points is very much like you want to, if you look at a, say, a parabolic manifold, and you want to construct a closed geodesic. So going back to Margulis' thesis, you know how to do it by taking, a long geodesic and let it flow for a long time, then use mixing, that you come after text. If you should not use the mixing, that once you flow long enough time, you'll be able to find to come back very close to where you started. And then there is a closing lemma. I mean, you can shift a little starting points and then it affects the ending point so that they collide. So there is a mixing plus closing lemma imitating Margulis' thesis is what allows us to do it. But now we need not to take just closed geodesic, but to kind of, if you want, a closed pair of points. Okay, so we use mixing and closing lemma to some multiple mixings, actually, in some sense, to get this to construct a pair of points. And actually, this not exactly pair of points, they're epsilon over r stitch, meaning that the boundary lengths are more or less 2r up to some epsilon, and also the pair of points are not exactly glued together. There is some epsilon of r perturbation. Now, so each pair of points which you construct is associated with 3 elements in the lattice gamma. The lattice gamma is fixed. So now we have we actually construct using this mixing and closing lemma lots of pair of points. All of them we choose some R, large R, which I have to choose somehow. There was in the background, there was this Sullivan map, which I skimmed over. This allows how to choose this epsilon. And you find lots of pair of points. All of those boundaries are of length roughly 2R, and each one of the boundary corresponds to some elements. So each pair of points, you get 3 elements, alpha, beta, and gamma. All of them are parabolic elements which roughly translate distance 2R. And they have this condition that alpha time, beta time, gamma is the identity. This is really an equality. This is not approximate. This is really the identity. This is important. So we show that you have lots of them, and then you want to use them to somehow construct a parabolic surface. So let's think what we're trying to do. A parabolic surface, so here you see a parabolic surface, and which is partitioned into lots of pair of points, to some finite number of pair of points. So we want to take if you want to think of it, that you start with a parabolic surface, partition into finitely many pair of points, and each pair of points, pi, you want to a map which associates to this pi some quasi epsilon r of r stitch pair of points, this approximate pair of points that we constructed, in such a way that if you have 2 pair of points here, pi and pj, let me enlarge it. So you have this pi and pj are 2 pair of points here which are adjacent along some boundary, then this quasi pair of points which they correspond to, this qi and qj, they'll have, each one of them has 3 boundary components, each one of this, so there are 6 elements from the lattice, but you want this, along this adjacent, they'll have the same common alpha, the same element from the lattice gamma. And suppose if you find such a collection, some surface, and a collection of partition of it into pair of points, so that any pair of points in the surface correspond to this quasi pair of parents or stitched pair of parents that we constructed in such a way that adjacent things have the boundary elements being the same, this immediately gives you a homomorphism. If you look at it, you get from this a homomorphism for the fundamental group of this surface into your lattice gamma. Just map every boundary of this pair of parents here to the corresponding element in gamma. Now, this would be a homomorphism, but it's not clear why. Well, first thing we have to show that such a thing can be found, but also it's not clear whether it will be injective, right? It's maybe you just took, one pair of parents and somehow maybe you fold it back and you just got something which is contractible. So you have to glue them in a way which is allows you to control things. And the idea is the following, that maybe I'll write here. So we have lots of pair of parents sitting inside our space. So think of just now as a symmetric space, and let's just assume right now that we are really working not with quasi pair of parents, but really with pair of parents, ideal one, perfect one. And so you want to somehow, when you'll be able to glue two things, you want to glue them here. If you look at the pair of parents, here's an ideal pair of parents. You want to glue here another pair of parents, so it has to go, maybe I'll change the color. You want to glue here some pair of parents, so the boundary has to match. And notice that if you have this pair of parents, then you can draw on it arrows in the middle of on each boundary component. You can put an arrow, actually 2 points. There are two special points. You can put an arrow pointed to the center of mass if you want these ideal triangles, and you want to glue two pair of parents if this arrow are going to be what we'll call a Kahn-Markovich twist of one another. You want to glue them if these arrows are, well, they want to point in the opposite direction and to be shifted with distance 1. That's the shift of distance 1 is something. This is an idea which goes back to the work of Kahn and Markovich. It's a beautiful idea that you have to shift by distance 1. It's really an insight. And this is I want to emphasize it. It's due to them, not to us, and it's really a very nice observation. Because what will be the problem? If you, ideally, you want to glue them with these two arrows. This arrow and this arrow will be just maybe even one next to the other, but really one the minus of the other. But you can't do it. You have to allow some perturbation. And if you do this perturbation along a narrow path, then they can accumulate and sink and collapse. The point that
Shahar.
Yeah, I have.
Shahar? No,
yes.
Yeah. Okay.
I think
please go ahead. You have another few minutes.
Yeah, if I look correctly, I think I have another 3 or 4 minutes, I think.
Now it is 2 more minutes officially, but
okay,
you can.
2 minutes. Okay, yeah. Okay, so what I'm saying that you want to glue them this way. Now there is one, okay, so let me just say, okay, so you want to allow things to be glued if these arrows are distance 1 from one another and point in roughly the opposite direction. Now, why can you find such thing? Now, what you do is the following. Remember, we have a finite collection of, we fix some big, huge R. So we have a finite collection of pair of parents. Each pair of parents has a boundary. Look at the boundary which appears. There's some alpha which appears, and there are pair of parents with them. Actually, there are going to be many of them. And the arrows are going to be, so you have this alpha gives you, if you think of it, you can think of it as if it gives you some closed circle, some boundary component of length 2R, and on it you have arrows. And these arrows are going to be equidistributed or close to, even in distributed, very close to being equidistributed. So in large R, they're converged to the equidistribution. And then you want someone to make a matching. So you have a graph. You have finite value versus each pair of parents. You look at its boundary, you look at who it can be connected to. You make a graph to whom it may be connected. These are the things which are distance epsilon from the Kahn-Markovich shift of them, twist of them. And you want to show that you can find the perfect matching. And this uses the Hall's marriage lemma. So Hall's marriage lemma is a statement, is a very beautiful and simple statement about graph theory, which speaks usually about bipartite graph. And you ask, when can you have bipartite graph, n vertices, and adjacency relation? When can you make a perfect match? And of course, you need that every set here the number of things it knows on the other side has to be at least the same size. Using this equidistribution that you get from the mixing allows you to show that the condition of some extension of the whole marriage lemma holds, and that's how you make this gluing. So whole marriage lemma give you the gluing, and then these things are, as I said, the gluing with the distance epsilon of R, and that allows you to lift things and build a map from the boundary, which is going to be what we call Sullivan map, which is this analog, this extension of being quasi-symmetric, which allows you to solve things in Jack, and I think I'm out of time. So I think I'll stop here since there is no more time. Thank you.
Okay. Thank you, Shahar, for the talk. Are there any questions?
I see that Mahan raised the hand. I don't know how to open this thing, but maybe if Mahan just
So Shahar, I mean, where did you use uniform lattices?
Where do you use in all this? Okay, first thing, let me say that uniform is probably not needed because in the case of SL2C, Jeremy Kahn and Alex Wright already proved it in the non-uniform case, just for SL2C. We use it in order to bound the distances. We have to take estimate on mixing, and then there is something which we need to, but it's more, I think, I don't think it's essential. Let's put it this way.
Okay, thanks.
This is something that I think we should be able to overcome. This being able to rotate the flip, what we call the flip condition, which I just maybe just moved over it very fast, but just saying that this automorphism can be realized by centralizer, that's something we don't know how to overcome. Even though in certain contexts, Kahn-Mark which overcame it for the Ehrenpreis conjecture. So it should be this also should be just technical.
Okay, thank you. Okay.
Any other questions?
Yeah, can I ask a question?
Sure.
Yes, please go ahead.
Yeah, so your construction proceeded by manufacturing 3 elements, alpha, beta, gamma with product identity in the lattice on the right hand side. I'm just calling right hand, G in the SL and C.
Yes.
So which kind of rose like a semi-canonical way from your pair of pants thing, right? Or am I?
No, you can find such elements very easily, of course, but the pair of pants allow you to find such 3 elements which are all, well, fancying they're all more or less the same shift. This is already not obvious. Why? First, you would take alpha and beta and gamma being the inverse of the product, right? But you want the cell one also to be roughly the same distance to R. And then, there is a lot of things which are hidden, especially about this last part, why it's injective. There we need it that it's coming from pair of pants, and we need this cheating about how to do it, not in a correct way, this vector, you have to be able to associate with this element, this vector here, and glue them in such a way. If I just take elements alpha, beta, and gamma which satisfy this relation.
Yeah, that's what my question is. The converse to you take any 3 elements, then do they arise from this pair of pants construction?
No.
Anyone else?
These are special ones.
Okay, these are special ones. Thank you.
Maybe I should, one thing I'd like to say is that Ursula Hammerstadt also have related results. I should have mentioned at the beginning. And I think Raghunathan has something to say.
Yeah. Yeah, can I ask my question?
Daniel? Sure, yeah, please go ahead.
No, I tapped on raised hand, it didn't work anyway. The question I have for Shahar is, can one do anything about higher dimensional hyperbolic manifolds? They're fundamental groups. Because this is, of course, you're using very special techniques for the surface case. But
so to find the final group, not find a surface, but finding a
hyperbolic 3 manifold, fundamental group.
Oh.
3 manifold, for instance.
I'm not sure it will be true, actually. I'm not sure it will work, but I have to think.
Well, you see, of course, all lattices except for SL3C, all lattices are going to be arithmetic. That doesn't help you do something, that's the complete classification after all.
I have to think. Someone will be very surprised if you can always find them, but I haven't thought about it really.
Okay.
I have to think, but I think maybe Mahan will know it offhand, but I think it's be very surprising if you can. I mean,
I will also be surprised if you can really, but
I think not, and I think it should be doable. Really. I think we should. Okay, let me think.
okay.
This is recording. I don't
Yes.
want to say a completely ridiculous thing, but I don't believe it.
Okay.
I think it shouldn't be hard.
Okay.
Okay, with that, I thank Shahar
Two
once again for
options
the
to
talk,
think about.
and also the people who asked the questions, making the session interesting.